All right, 2.4, operations with functions. So today we're going to take a look at some different function operations. Some of them are very straightforward. They work just like you expect them to work. And then there's one that's a little bit unique. So we're going to start with the straightforward functions. So the first ones, I'm not even going to tell you how to do them because I think you can probably guess. So we've got two functions. F of x is x minus 3, and g of x is x squared minus x. So you've seen this notation before, right here, where we put the number 3 into something, right? You plug in 3 for x. So what do you suppose this notation means? Say it for me again louder. Okay, you're going to plug it into both the equations, and then what are you going to do with them, Maggie? Add them together. Exactly. So you're going to plug it in here, and you're going to plug it in here, and then you're going to add the results together. So in a very real sense, this is exactly what you just said. It's f of 3 plus g of 3, and we're going to plug it into each of them and add the results together. So if I plug in 3 to f of x, I would have 3 minus 3. And if I plug in 3 to g of x, I will have 3 squared minus 3. So 3 minus 3 is 0. 3 squared is 9, and 9 minus 3 is 6. So I end up with a grand total of 6. It's just what you would expect, right? It says add them together, you add them together. It says put in the 3, you put in the 3. So what do you suppose is going to happen on the second one? You're going to subtract. I know this is like audience participation, even though you think it sounds silly. I get it. Yeah, we're going to subtract, and we're going to plug in this time the number 5. Always with subtraction, we want to be a little bit careful with our signs to make sure that they distribute through anything that's coming after the subtraction, so we'll be a little bit more careful here. But yeah, this is f of 5 minus g of 5. So for f of 5, that's 5 minus 3. And then put the subtraction sign here, and I'll put a bracket just so that I'm careful to distribute my negative. And then I need g of 5, which should be 5 squared minus 5. So 5 minus 3 would be 2. And then I'm going to subtract, what's 5 squared? 25, and 25 minus 5 is 20. And then 2 minus 20 gives me negative 18. Okay, all working just like we expect. What do you suppose the third notation is telling you? Multiply, right? And plug in the number, in this case, negative 2. So we're going to take f of negative 2, and we're going to multiply it by g of negative 2. So we have negative 2 minus 3 times, and then I'll bracket this in again just because I have a squaring inside of there if we might need it. So I have negative 2 like that squared, and then minus negative 2. So lots of negatives in the second part can throw us off, but we'll be careful. Negative 2 minus 3 is negative 5, right? Yeah. And then what happens when I take negative 2 and I square it? I get 4, and this says minus a negative, which changes to plus, so now I have 4 plus 2, which is actually 6. Negative 5 times 6 would give me negative 30. Any questions so far? Okay. D tells me what am I going to do? We're going to divide. Exactly. So we're going to take our value and plug in negative 4 this time. And we're going to divide f of negative 4 divided by g of negative 4. So again, this is negative 4. Don't really need the parentheses, but negative 4 minus 3 on top. And then I have negative 4 squared minus negative 4. Got that double negative going on again on bottom. So what's my numerator? Negative 7, right? In the denominator, I've got minus and negatives. This is going to change to plus. But what's negative 4 squared? 16. And then now I have 16 plus 4, which gives me 20. So I have negative 7 over 20. If it reduced, we would reduce it there, but it's odd on top, even on bottom. I don't have any factors in common, so it's done. Now E starts to look like what I just did back on A. How is E different than A? Yeah, there's just an X. On part A, I had a 3 next to it, right, over here. But on part E, I just have an X next to it. So it's actually, I kind of think, easier because you're not actually plugging numbers in. You're just doing the same thing, in this case addition, but you're doing the addition without actually having to do any evaluation. So there's less going on, to be honest. So I'm going to take my f of x equation, and I'm going to add it to my g of x equation. Well, f of x was x minus 3, and g of x is x squared minus x. So we're doing it without numbers, but everything works the same from the simplification of all the algebra that we've done in the previous chapters in our book. So if we don't pay attention to if we just go from left to right, here's an x here and here's a negative x here, so what's going to happen? Yeah, those add to 0, so those become non-existent. I have a negative 3 at the front. Whoa. Hit the wrong button. Negative 3 at the front, and I have an x squared here at the back, right? So it might be a little bit more pleasing, move this over here, if we would change the order and write this as x squared minus 3 instead. To be honest, if you left it as negative 3 plus x squared, I'd be just fine with that. But my math lab might make you put it in order. I'm not sure. Make sense? So what do you suppose we're doing on part F? Subtracting, yeah, it says subtraction, so I'm going to subtract. Again, without the values plugged in, right? Just as it is with x. So this is f of x minus g of x. So f of x is x minus 3 minus g of x is x squared minus x. So we do need to distribute the negative through, agreed? Yeah, we will. So as I distribute my negative through, it will change both of those signs. So I have x minus 3, and then I have minus x squared, and I have plus x. So be careful with your negatives. If we're collecting like terms, we have x's that don't cancel this time, right? So I'll start with the highest power, just because it's a little more pleasing. Not because it has to be done, but negative x squared. And then I've got some x's. How many x's do I have? Yep, 2x. And then my constant is negative 3. It's all good? Okay? So what do you think the next slide's going to tell you to do? Multiply, right? Add, subtract, multiply, divide. So we're going to do the same thing. Multiply, divide. So let's do addition or multiplication. So my f of x is x minus 3. And my g of x is x squared minus x. But actually to multiply these this time, right? So if like foiling, first, outer, inner, last, or distribution, whatever language that you would like to use. So if I multiply my first terms together, I have x cubed. My outside terms give me negative x squared. My inside terms give me negative 3x squared. And my last terms give me a positive 3x. And then we'll combine any terms that are alike, which there are in the middle. So x cubed minus 4x squared plus 3x. Okay, all good? Okay, so our last one in this particular set with these functions, which we're probably getting tired of, I know I am, is to divide them. And we're dividing them without plugging any values in. Now there's one extra little condition on the bottom here where I wrote, just so that you could make sure that notice it, that says domain. We have to pay particular attention to that, so we'll come back to that in just a second. But I'm running out of space. Again, it's division, so it's f of x over g of x. f of x is my x minus 3, and g of x is my x squared minus x. If it factored, which the denominator does factor, right? I mean, like, I could rewrite this with the x pulled out, and it would be x minus 1. But it doesn't cancel with the numerator, so I don't necessarily have to rewrite it. Are you with me? Looking for cancellations is the only reason why I would need to factor anything at this point. The other reason that I might want to factor anything is to answer the question about domain. So anytime I do division and I have variables in the denominator, I potentially have things that x cannot equal. What are values here that x cannot be? Somebody give me one of them. Actually, x can be 3. The numerator is okay to be 0. It's the denominators of the problem. So x cannot be 1, and x cannot be 0. So if x were 0, I'd get a 0 right here. If x were 1, I'd get a 0 right here, right? So those are the two values that x, in this case, that x cannot equal. So my domain is that x cannot equal, actually I'm running out of space, let me shift it a little bit, but like you just said, 0 and 1. Anything else is fine. It's okay for the numerator to be 0, but not for the denominator. Notice we didn't have to do that on any of the previous ones because we didn't have any denominators with variables in them. Agreed? I mean, we did have a denominator on one of them, but it didn't have a variable in it, so I didn't have any chance of being equal to 0. Okay, so addition, subtraction, multiplication, division, those are operations on functions, are just like you would expect them to be. The other operation on functions is not necessarily what you would expect or not expect. It's just something that's a different operation. You've been doing addition, subtraction, multiplication, division since 1st to 3rd grade. So those are very familiar operations. This operation is not quite like that. So this operation is called composition of functions. It looks a little bit like the word fog. The O kind of in between is actually much smaller, almost like a multiplication dot, but it is hollow. And what it actually means is that you take the equation or the value that g of x is, and you plug it into the f of x function. And we'll do several examples to show that. So it's sort of like these embedded values that we're working with when we get to composite functions. I changed my functions just so that we could have a little bit of variety. Now I have f of x is square root of x, and g of x is 1 over x plus 3. Okay? So this says, according to the definition, that I can rewrite it like this. Okay, so that's the first thing to do, is to rewrite the definition with your values. F, G, and 2. And then just like with order of operations of everything else, we work from the inside out. So on the inside is the part here that says G of 2. Okay? So I'm going to go over to my equation. And you can even write this as a separate step if it makes you feel better, right? Do step number 1. Let's find G of 2. I'll write it this way, at least for this one. And it says I need to take the G of x equation, which is 1 over x plus 3, and I need to replace the x with 2. So this is 1/5. Right? That's nothing new. Just evaluating. The new part then says that I take this solution that I just found, 1/5, and I plug it into the equation for f of x. So my second step is now to find f of 1/5. And again, the 1/5 is coming from here. Whatever the answer was the previous part of it, you're using that answer as the input now. So on my f of x equation, that's the square root function. So I now have the square root of 1/5. Okay, so square root of 1/5 is the same as the square root of 1. So we're going to simplify over square root of 5. What's the square root of 1? 1, so that's cool. What square root of 5, however, doesn't work out very nicely, right? It's an irrational number. So we would rationalize the denominator, which we talked about back in chapter P. So square root of 1 is 1. Square root of 5 you can't simplify in a more concise way. But square root of 5 times square root of 5 is 5, which is why we wanted to do that to begin with. So the final answer to your question of all of it composed together is square root of 5 over 5. Now on part B, what we're going to do is we're going to do the same 2, but instead of starting with the g function, we're going to start with the f function. So your first step is always to rewrite. So the first thing I'm going to do is to rewrite this as g parenthesis f parenthesis 2. That's how it rewrites. And then we're working from the inside out. So step number 1 is to find f of 2. Okay, well, the f of x function is that square root function. So that's square root 2. And there's no simplifying. I can't rationalize that. It doesn't have a denominator to worry with or anything. So we just have square root of 2. And that now becomes the input into the other equation. So now I have g of square root 2, because this square root of 2 is replacing f of 2 inside. So now I go to my g of x equation, which is 1 over x plus 3. And I get 1 over square root of 2 plus 3. Okay, so does that make sense so far? But now I have square root in the denominator, and it's not quite as friendly as the last square root in the denominator because there's addition, right? So you guys remember how we get that square root to rationalize? Conjugate's exactly right. So I would have the square root of 2 minus 3, and I would do it on the top and the bottom. That's the conjugate. On the top, it's just times 1, so it's square root of 2 minus 3. And please don't tell me that's 1 or negative 1. One of them is underneath the radical, the other one's not. They cannot be combined, okay? But in the denominator, when I distribute this and multiply it all out, I will get something that's very nice. And the reason I will is because the inside and the outside terms, they're match. But one's positive and one's negative, so they cancel. And so I don't have those terms. I only have the first terms. And what's square root of 2 times square root of 2? 2. And then I have my last terms. And what's 3 times negative 3? Yeah, I've got negative 9 on that one, right? 3 and 3, and then I've got the negative, so negative 9. The numerator is still square root of 2 minus 3, but then my denominator is negative 7. And there's nothing that we can do on that one either, because there's nothing that cancels out of every single piece of it, right? Okay, so just like we did back with the addition, subtraction, multiplication, and division, I started out by showing you what happens when I have a number next to it, right? We talked about how we plug in the number when we do all that jazz. Well, the next thing I showed you is what happens when there's an x next to it instead. We've done the same thing with composite functions. This is composite functions when I have a number next to it. Now I'm going to show you what happens with those same functions when I have an x next to it. Okay? So your first step looks exactly the same. You're simply going to rewrite. This is f of g of x. There's just not a number inside, there's an x inside. So far, so good? Okay. Now, if you think about what we did and we sort of mirror it here, the first thing I did is I wrote down what the inside function was with the number in it. So I'm just going to write down what the inside function is with the x in it. So that's 1 over x plus 3, right? That's g of x. And then the second thing I did is I took that value and I put it inside of the function that's on the outside, f of x. So this is going to say 1 over x plus 3. So f, and then it's 1 over x plus 3. Just like on the previous ones I had, whatever number I got, and I put it inside. Now this notation always means that whatever is inside replaces the x in the equation f of x. Okay? And when it's numbers, we feel very comfortable with that. When there's variables, we feel a little bit less comfortable with that. It looks weird to us, and you get that. But the process is actually the same. The square root looks like that, and then the x gets replaced by what's in the parenthesis next to f. So in this case, it's 1 over x plus 3. Okay, is that okay? Now, the cool thing is we don't have to do a whole lot of simplification for this. I am going to separate the radical from the top and the bottom because, whoops, there's supposed to be a 1 on top. Because the top is so nice. What's the square root of 1? Yeah, it's 1. And the cool thing is that when we had radicals with just numbers underneath there, I said you got to rationalize, right? Remember that? Well, if there's variables underneath there, you don't. So it's a lot easier. You actually get to leave it there. There's no rationalizing going on. So you actually have fewer steps when there's not a number next to it. Now the domain is an issue because, again, I have a denominator, right? Anytime I have a denominator, we got to have issues. We potentially have issues with the domain anyway. There are things that the denominator can't be. Any ideas? Well, the denominator can't be 0. I said that totally wrong. There are things x can't be is what I wanted to say. You were about to tell me something. Somebody said something about negative. Was that you, Maggie?
Yeah, there just can't be negative.
Right. That's really important to notice. I can't have a negative underneath the radical, right? That's a square root issue. What else can I not have since I have a denominator specifically? 0. I can't have 0 in the denominator, the whole denominator, right? So what I really need is I need whatever goes underneath this radical not to just be not negative, but it can't be 0 either, right? Because the square root of 0 would be 0. So what's underneath the radical, which is x plus 3, needs to be greater than, strictly greater than 0, not just greater than or equal to. And we can solve that, right? Just subtract, almost said add, subtract the 3 to the other side. So we need values that are bigger than negative 3. So that's my domain. Over here where it said domain, my domain is that x is greater than 3. Negative 3, sorry. That negative in there. Negative 3. Okay, now we're going to go in the opposite order. I didn't make mention of it. Perhaps I should have. Notice the order matters here, right? There's a lot of operations that we have that order doesn't matter, right? If you add things, 5 plus 3 is 3 plus 5. But subtraction order matters. 5 minus 3 is not 3 minus 5. Here, the order matters as well. F composed with G, and G composed with F did not give us the same answer. And you might be tempted to think, well, that had something to do with the numbers that were involved, and that's not necessarily a bad thought. So we're going to see what happens when we have X involved instead, more general kind of a form, and see if we get the same answer on that one. So we've done half of this. So now we're going to look at the other half. So we're going to do G composed with F of X. So again, step 1 is to simply write out what is F of X. And what is F of X? It's the square root of X. Yeah. And then step 2 is to take my G function and to replace the inside with square root of X, because that was the output I had on the previous step. And again, what that means is that now I go to the equation for G, which is here, and everywhere I have an X, and there's only one of them, I will have a square root of X now instead. So I have 1 over square root of X plus 3. This is good. And again, I don't have to rationalize. It's good stuff. I do have to deal with the domain, though. There are values that X cannot be. Now, it's different than the last problem because the 3 is not underneath the radical, right? The 3 is outside of it. So, I can't have a negative in the whole, I can't have a 0 in the whole denominator. That's true. But I've also got the radical part, which Maggie had mentioned to us before. We can't have negatives underneath radicals, right? So let's deal with the negative underneath radical part for a moment. So if I can't have a negative underneath the radical, what kind of values potentially do you think then that X needs to be? It can't, yeah, greater than 0. And this time it actually could equal 0 too, because the square root of 0 is 0. And what's 0 plus 3? 3. So that's an okay value, right? I didn't have that ability over here because I was taking the radical after I did the addition or subtraction. And here I don't have that. Now, here's the cool thing. I'm adding 3 to this denominator, right? Like the square root part of it. So whatever number I put into here, square root of X, don't I always get out a positive number? I do. Square root of X would be like numbers always bigger than 0. And if I say take something that's always bigger than 0 and add it to 3, do I ever get 0? No. So I don't have to worry about this denominator equaling 0. It's already not going to because I've got the addition with the radical. So it only had to deal with the radical part of it, and it took care of that. Now pause for a moment. Don't erase yours, but just consider with me. If this had been a negative instead, would there be an additional thing I couldn't have? There would. X could not be 9. Because if X were 9, I mean, X, it still couldn't be negative, right? It still has to be bigger than or equal to 0, but it still couldn't be 9 because I would get the denominator as 0. So it has to be you have to be very careful. That sign here mattered here because it was addition. I didn't have anything that was able to make the denominator 0. But if it had been subtraction, I would have. So on our domain on this one, our domain is just that X is greater than or equal to 0. Okay, there's one more piece of information in this section. So what we've just done is called composition of functions. We're mushing them together. That's a very technical math term, mushing, just so you know. It's not, right? That's what we're doing. We're shoving them together, right? We're mushing them together. Well, we're going to go and we're going to also separate them apart. This is called decomposition. Okay? So, what's that? No, nothing. Okay. Decomposition means breaking them back apart into pieces. Okay? There's often a very natural way to do that. Sometimes there's more than one way to do it. Here would be an example that there is more than one way to do it, but one of them is maybe a bit more natural than the other one. So if you can identify a portion of the equation that is a standalone function by itself, like notice right here, there's a square root of x. And then it has other stuff happening around it, right? That would be a good inside function. So my function that's on the inside right now is g. It's just listed separately, right? So if I were to rewrite this like I have been, g's inside. So that square root of x is a very nice place for us to actually start. Square root of x. That's my inside function because it looks like it's inside of the other things going on around it. And if I do that, oops, it's not f this time, it's h, isn't it? And if I do that, then where am I going to stuff the square root of x into? Well, it needs to be next to a 3, and it needs to have a -1 after it, right? And the placeholder is always x. So imagine now if you took this square root of x and you shoved it in right here, you'd have the same thing you started with, right? You would. Now there is another one here that I'm going to mention as another option, just because I want you to see that sometimes there is more than one answer and there are more than one correct answer even, right? It's correct. What we could do is we could make g of x 3 square root of x. It would be okay. If I did that, the only thing that I didn't do was the -1 part, right? It is. And so the placeholder that I would need is always x. And can you imagine taking the 3 square root of x and you shove it into where the x is? And again, you'd be back to where you started with. So the key is always taking a look at the function you have and identifying a portion of it that is a function that's standalone on itself, right? It's something on its own. Like maybe it's an x squared. That might be what you have. Or maybe it's something that's happening with, like I did, like a 3x. You could do something with that, depending on what's going on. Okay, so that's it for section 2.4.